Here is the problem. We are given pole zero plots for two transfer functions g1 and g2, both with constant coefficients k equals -2. g1 has one pole at -0.2 and one zero at +0.2, both on the real axis. G2 has the same real pole and zero, plus a pair of complex conjugate poles at -0.4 plus or minus 0.3 j. We need to write the transfer functions, find relative degrees, check stability, and match G2 to a state space model. Part A. Write the transfer functions from the pole zero plots. For G1, we have one zero at s equals 0.2 and one pole at s equals -0.2. With k equals -2, the transfer function is G1 of s equals -2 times s minus 0.2 divided by s plus 0.2. For G2, we have the same zero at 0.2, the same real pole at -0.2, and complex conjugate poles at -0.4 plus or minus 0.3 j. The complex pair gives the quadratic s squared plus 0.8s plus 0.25. So G2 of s equals 2 times s minus 0.2 divided by the quantity s plus 0.2 times s squared plus 0.8s plus 0.25. Part B. Find the relative degree. The relative degree is the number of poles minus the number of zeros. For G1, one pole minus one zero equals 0. A relative degree of 0 means this system is not strictly proper. For G2, 3 poles minus one zero equals 2. G2 is strictly proper with relative degree 2. This matters because a system must be proper for physical realizability. Part C. Check stability. A transfer function is stable if and only if all poles are in the open left half plane, meaning all poles have strictly negative real parts. For G1, the only pole is at s equals -0.2. Its real part is negative, so G1 is stable. For G2, the poles are at -0.2 and -0.4 plus or minus 0.3 j. All three have negative real parts, so G2 is also stable. Note that the zero at +0.2 is in the right half plane. This is a non-minimum phase zero, but it does not affect stability. Stability depends only on poles. Part D. Which system matrix matches G2? The poles of G2 must be the eigenvalues of the system matrix A. The poles are -0.2, -0.4 plus 0.3 j, and -0.4 minus 0.3 j. Matrix A1 is 3 by 3. Computing its eigenvalues from the characteristic polynomial, det of si minus a1 gives s plus 0.2 times s squared plus 0.8s plus 0.25. The eigenvalues are -0.2 and -0.4 plus or minus 0.3 j. These match the poles of G2 exactly. Matrix A2 is 2 by 2, so it can only have 2 eigenvalues, but G2 has 3 poles. Not suitable. Matrix A3 is 3 by 3, but its eigenvalues are -0.2, -0.4, and -0.3, which do not match. The answer is A1. Let us recap. From the pole zero plots with k equals -2. G1 equals -2 times s minus 0.2 over s plus 0.2 with relative degree 0. G2 equals 2 times s minus 0.2 over s plus 0.2 times s squared plus 0.8s plus 0.25 with relative degree 2. Both are stable because all poles have negative real parts. The 0 at 0.2 is non-minimum phase, but does not affect stability. For the state space match, only A1 has eigenvalues matching G2's poles. 4 parts. Pole 0 analysis complete. Done.